Welcome to lesson 6 of this series of the Astrophysics unit of the AQA A-level physics course. Go back and look at the other videos if some of this is not going to make sense to you, but this one, if you're looking for a revision or first time learning, this one I'm just going to cover distance scales. So look at the specification here, only 3.9.2.2, just those bottom parts there. And I've already been over n minus m equals 5 log d over 10. So I've done that. Go back and look at that. I'll do a little bit of recap, but this is generally dealing with distance scales. It says parsec and light year here, but I'm also going to include astronomical unit as well, which has featured in some of the past exams. So if you think, hang on a second, he's doing more than I need to, I always do this just in case, because examiners like that. They'll stick in something, and I don't even be surprised when the exam comes around, because exams are not places for surprises. Okay, so this is what we've covered so far. Great revision activity is just pick 3 of these, pick a random one, just splurge everything you know, check it against your notes. So for instance, luminosity. What is the unit of luminosity? Oh, I split my sides with humour. And then what's absolute magnitude? That's from last lesson. Why do we put telescopes high and dry and a long way from civilization? And it's why they're there is the important bit. Can you draw a Cassegrain telescope? Do you know what chromatic aberration is? 1b, 2r. So, distance scale. There's 3 orders of magnitude here. Astronomical unit is the mean distance from the Sun to the Earth. Light year is the distance travelled by light in 1 year, and that's the speed of light, 3 times 10 to the power of 8 meters per second. And then a parsec, which is the distance at which 1 AU subtends in 1 arc second. And you can see why I've included astronomical unit, because you can't understand parsec without understanding what an astronomical unit is. Astronomical unit, of course, refer back to the top here, which is the mean distance to the Sun from the Earth. So why do we have 3 measures? Well, we measure different things in the universe. If you want to measure distance to the nearest planets, then of course AU is a sensible way of doing it. If you want to measure the distance to the nearest stars, for instance, light years is the sensible way of doing it. If we want to measure the distance to the nearest stars and maybe some distant stars within our galaxy and maybe to other galaxies, then we'd use parsecs and in some cases megaparsecs as well. And those are generally megaparsec. A million parsecs is the unit that we use for distances to the galaxies, both near and far. So if we move on, astronomical unit. So here we are. Here's the Earth's orbit around here at 1 AU. Venus's orbit is about 0.7 AU, therefore the distance between them is 0.3 AU. And you can see astronomical unit is 150 million kilometers, so that's 150 billion meters. Why is it a mean distance? Because the Earth's orbit is not circular, it's just elliptical. Not a great deal elliptical and not enough to make a great deal of difference. The tilt of the Earth is actually a much greater factor in the temperature of the Earth and where we are in the ellipse of the orbit. But nevertheless, that's the AU, mean distance from Earth. Light year is this number in meters. That's an awful lot of significant figures. This is given on the formula sheet, by the way, so don't worry about this. You don't have to remember these things, but you do have to convert between them. So, for instance, calculate the number of seconds in 1 year. Really common calculation. A lot of students get a bit scared about this, but remember, 365. We'll call it 365.25. Why is it 365.25? I hear you ask. Leap years. It's because the year is not 365 days long. It's 365 days and a quarter, and that's why we have 366 days in a leap year. And then calculate the numbers in a light year by multiplying the number of seconds in a year by the speed of light. So therefore you just do those together and you end up with that rather large number at the top, which is 10 to the 15 meters. Closest star to Earth, other than the Sun, is 4.3 light years away. Convert that to meters. There it is. I think then you can get the light year measurement. Andromeda is 2.2 million light years from Earth, and you can see that doing these gets you a handle on the sort of distances. So nearest galaxy, major galaxy anyway to us, Andromeda galaxy, 2.2 million light years. And the diameter of our own Milky Way galaxies is 100,000 light years. And you can see actually Andromeda is only a few hundred times bigger, times further away than the diameter of the Milky Way itself. So it's a very near neighbour, and that gives you an idea of how near galaxies are to each other. Incidentally, Andromeda is moving towards us, so you know, it's going to take a long while, but nevertheless, it's still on its way over here. Great, I mean, great to see the collision of galaxies. Well, the collision of galaxies are odd because very few stars actually hit each other. But anyway, by the by. What you indeed need to know is the conversions between them. So that's all well and good, conversion between them. But the next one is probably the trickiest, which is a parsec. Now, a parsec, irritatingly, Star Wars, was it Empire Strikes Back? I can't remember. One of the Star Wars films, anyway, mentions about parsec, and they suggest that it's a time unit. It's not. It's a distance unit. Films always irritate scientists. And there it is. And you can see it's a bit bigger than light years. So it's 10 to the 16 meters. And this is how it goes. So 1 parsec is the distance at which 1 AU, remember that's the distance from the Earth to the Sun, hence SE, subtends 1 arc second. And 1 arc second is 1/3600th of a degree from here. So I'll say that again. So 1 parsec is the distance at which you recede that 1 AU into the distance, and that's when it subtends 1 arc second. So get your calculators out. How many parsecs are there? Sorry, how many light years are there in a parsec? And how many astronomical units are in a parsec? All these things need to be calculated to get you an idea of this conversion between them. So that's it. Have a good stare at that picture because that is a really important one. Notice it's actually very similar to the angular size calculations we were doing before. So therefore your A1 AU over 1 parsec will give you 1 arc second. So if you want to do all that in meters, because it's got to be in the same units, then by all means go ahead and check it. Make sure that I'm not telling a porky, and I am telling the truth. Oh, sorry, I just rewind there. There you go. So therefore the answer was just skip by. Never mind. Parallax, not on the specification, but nevertheless important to know. Basically, stars, nearby stars, can move in relation to distant stars as the Earth moves around, just to get you an idea that the stars are not on this fixed globe like they used to think back in the 1500s. Stars do move as the Earth moves around the orbit of the Sun here. If a star is near, it will appear in different places on the sky in relation to distant stars. And so therefore, if you fancy doing some working out the distance to a star, you can get it by knowing what the radius of the Earth's orbit is. There it is in meters. You know, and then working out what this triangle here. So therefore, you've got a nice distance. You want this distance here. I've got this distance here. I can work out what the angle at which it subtended its backside. So it's half the angular distance it moved. Yeah, it's not a specification, but I always like throwing it in there because parsec's in there. They're bound to ask you something about that sooner or later. Okay, much more typical question now. NGC 54414 is a typical spiral galaxy, the constellation Cumulonimbus. It is about 55,000 light years in diameter and approximately 60 million light years away from Earth. So you can see both of them being given in light years. Right, convert them to AU. Remember, an AU is smaller than light years, so that's going to give you a bigger number. Convert to parsecs. Parsecs are bigger than light years, so it's going to give you a smaller number, roughly by a factor of 3. Now, what's its angular size? You can do that in any of these units as long as they're exactly the same. So with that one, just put 55,000 over 60 million because they're both in light years, and you'll get the angular size in radians. So it's in radians. And then, of course, a really good exercise is what size of optical telescope do I need to observe at one resolving power of that. So in other words, I need to know what the wavelength of optical light is. So go for 500 nanometers. That's about in the middle. 600 nanometers is red, 400 is bluish. So therefore, go for 500 nanometers. You know that resolving power, so the angular resolution, resolving power, same thing, remember, is 1 times 10 to the power of minus 7. So make that equal to your wavelength, 500 nanometers, divided by that diameter, which we want. We want the diameter. So just swizzle that round, and you can get a reasonable diameter for those. So stop the video, do those calculations and get comfortable with all the different numbers that we've got. And that's it. So just to recap here, all the different bits and pieces we've done so far. Again, revision activity. Stop the video. Pick 3 that you didn't pick before and just do everything about it. This is the only way you're going to learn it. You're not going to learn it just by listening to me and doing this, sitting there passively staring. What you got to do is write things down, and you've got to do it now. So do it now. Pick 3 of those. Work out what angular size was. What was a parsec? What was absolute magnitude? How do you draw a Cassegrain telescope? Do them on a piece of paper now. Hold them. Put them into a folder. Keep them, and then you'll be on your way to become a proper student. Proper students do not just watch videos on YouTube. They do the work. Okay, so here's a real recap, 6 marker. If you've got, I says with a partner here, if you're watching this in a classroom, but if you're watching this on your own, then you've got to construct the perfect 6 marker for this. Different types of telescopes. Describe 3 different parts of the electromagnetic spectrum and factors you need to take into account the sighting and size of the telescopes. Sighting, high, dry, far away, if that's relevant, or even high in space. And the size of the telescopes, theta equals lambda over d. That's how you decide the size of a telescope. So the smaller the wavelength, the smaller the telescope can be. The larger the wavelength, the larger the telescope, to get that angular resolution, the resolving power, to get that really down. Theta equals lambda over d. That's the one you need to be able to do. Calculation and also arguments for 3 different parts of the electromagnetic spectrum. Do, UV, visible, and radio if you want. And then knowing those different parts of it is really important. So stop that, do your 6 marker. It should take you about 6 or 7 minutes. And I'm going to just go to the mark scheme in 3, 2, 1. And there it is. Stop the video, and you can look at all the different parts that they've used there to be able to assess that. And that's it for this one. It's only a shorty, and then we'll go on to the next lesson.